Have you ever wondered what makes up the screen of your phone?
Or your televisions, computer monitors, and other fascinating electronic devices?
How about the precious jewelries embedded with sapphires, rubies, diamonds, and other high-priced precious stones?
Or even on the glass where you drink or the glasses of windows?
Minerals are everywhere, from the ground touching your feet to the most precious possession you wear, and even to the billion-word space rums wandering in the universe.
Minerals make up almost everything. It existed even before life, an art of nature, and now coexisting with another masterpiece, the humans.
Now, let us take into a deeper understanding on what minerals are, and the only door to its dimension is through mineralogy.
For a couple of minutes, we'll be making ourselves as mineralogists with enthusiasm, like overlooking at the spectrum of knowledge forever known crystal.
Minerals consist all of our known rocks present in the Earth's outer layer called crust. These are naturally occurring, having definite and varied characteristics and properties. Through the years, minerals have been notable for their specific uses, marking the importance on humans. Significantly, it is needed for us to study minerals present in our day-to-day lives, and that is the role of mineralogy. Mineralogy is the study of minerals, dealing with the detailed mode of formation, composition, occurrence, types, association, properties, uses, etc. A science dealing with the minerals and ways on how we can distinguish them. Prehistorically, about 7000 BC, humans already had their own concept on the use of minerals, most commonly the use of lapis lazuli, known as gem, which was believed to have magic and sacral meaning. Furthermore, in the known history of human civilization, the emergence of the use of minerals, or the precious stones, notably started and widely observed in the eastern regions, such as China and India, particularly for traditional and religious purposes, more than just ornaments. Maybe because of how they appear, crystalline in nature. Today, we have a more profound knowledge and understanding of the minerals and the concept of mineralogy, becoming an entry point to it. There are four major heads in which mineralogy is treated under. The scopes of the study is divided into what we call crystallography, physical mineralogy, chemical mineralogy, and descriptive mineralogy. All are essential fields of studying the complexity of minerals. First, we have the crystallography. It discusses the crystals in general, specifically in the crystalline forms of mineral species. Second, we have physical mineralogy. This discusses the physical components, characteristics, and properties of the minerals. Third, we have chemical mineralogy, which presents the general principle of chemistry as applied to mineral species, especially in the chemical composition and characteristics of minerals as chemical compounds. And lastly, descriptive mineralogy, which deals with the classification of minerals and the description of each species with its varieties. Mineral. It is a naturally occurring inorganic substance with distinctive physical properties and has a more or less definite chemical composition. Minerals are the units that make up the rocks on the outer shell of the earth known as crust. Moreover, James D. Dana developed the first widely accepted concept of mineral classification, which had been the foundation of the one we use today. According to Dana, mineral is defined as a naturally occurring, solid, chemical substance formed through biogeochemical processes, having characteristic chemical composition, highly ordered atomic structure, and specific physical properties. From this definition, we can certainly assess that in order to classify a substance as a mineral, it should satisfy 5 characteristics in which minerals fall under. What are the 5 characteristics of minerals? First, minerals are natural. You must find minerals in nature. Substances concocted in laboratories don't qualify. Although some laboratory products resemble minerals, they are not considered as true minerals. We must take note that the minerals we used as ornaments or jewelries even are conforming the characteristics of minerals. Still, they are not considered as true minerals, for they underwent already a synthetic process and not a mere natural process by which minerals are defined. Second, minerals are inorganic. Minerals don't belong to any class of organic compounds, which include substances such as carbohydrates, proteins, and fats made by living things. Almost all known minerals come from inorganic processes, activities that living things cannot carry out. We can certainly and possibly classify if a substance is a mineral or not by assessing the presence of carbon. Carbon consists all organic substances. Though some minerals contain carbon, still it depends on the kind of element they bond with. Thirdly, we have minerals are solids. Minerals cannot be liquids or gases. They exist only as solids, a state of matter that possesses a high amount of order. Minerals must have a clearly defined volume and shape, and fixed molecular structure, which cannot be compressed any further. We must take note that minerals are structurally rigid, which means that the particles within the minerals don't move around. Fourthly, we have definite chemical composition. Each mineral has its own specific combination of atoms that cannot be found in any other minerals. One of the common examples is salt, a mineral of course. Salt is consisted by sodium and chlorine ions bonding together in a distinctive and definite repeating pattern, which cannot be found in diamond, which on the other hand is consisted only of a single type of atom, which is carbon. And when carbon comes together, it forms an extremely tight bond, making it the hardest substance on Earth. And lastly, mineral has crystalline structure. Minerals form crystal that contain repeated arrangements of atoms or ions. Each repeating part of a crystal is a unit cell, which takes on different shapes depending on the size of the ion or atom and how it attracts other particles. Minerals have crystalline structure which can be formed in 2 different ways, one of which is through magma or lava from volcanoes, which can crystallize to form minerals. Minerals can also be crystallized in the oceans, when water deposits solutes in certain areas, and when water evaporates, crystals appear. We already discussed the 5 characteristics of minerals, in which we had mentioned that minerals are solid. Solid is characterized to have definite shape, volume, mechanical strength, and compressibility and rigidity. We have 2 known classifications of solid when it comes to structure. the crystalline solid and the non-crystalline solids or the amorphous solids, where we will be comparing their features. What are crystalline solids? These are solids with highly ordered arrangements of their particles, such as atoms, ions, and molecules in microscopic structure. The features of crystalline solids are: these are considered as true solids. Its particles are arranged in a repeating pattern. They have a regular and ordered arrangement resulting in a definite shape. They have a sharp melting point. They also have definite heat or fusion. They are also anisotropic in nature. And when cutting a sharp edge, the two new halves will have smooth surfaces. And lastly, they are rigid solids, and applying mild forces will not distort its shapes. While the other classification of solid according to structure is the amorphous solids. These are solids in which the particles are not arranged in any specific order, or the solids that lack the overall order of a crystal lattice. Its features are: these are called pseudo-solids or super-cooled liquids. Particles are arranged randomly. They do not have an ordered arrangement resulting in irregular shapes as compared to crystalline solids. They do not have sharp melting points. The solid tends to soften gradually over a temperature range. They do not have definite heat of fusion. And unlike the crystalline solids, they are isotropic in nature. And when cutting with a sharp edge, the two resulting halves will have irregular surfaces. And lastly, they are not rigid, so mild effects may change the shape. Let us have a deeper understanding on what minerals are by focusing on crystal structure. The elements of crystal structure are fundamentals for us to fully understand and determine what minerals are. What are the elements of crystal structure? First, the crystal faces. Crystals are bounded by flat surfaces, which are known as faces. A crystal may have only two faces of the same geometrical shape, or it may have up to 48 faces of a combination of geometrical shapes. We can say that crystal faces is how the minerals appears physically. Number 2, the edge. The line of intersection formed by any two adjacent faces in a crystal is called edge. Number 3 is the solid angle. The points of interaction formed by 3 or more adjacent faces in a crystal are called solid angle. Fourth, the interfacial angle. The angle between normal of two adjacent faces is called interfacial angle, which can be measured using a contact or reflecting goniometer. Fifth, the distortion. In spite of perfect internal atomic arrangement, sometimes crystals develop faces of different sizes, shapes called distortion. We can say that minerals of different sizes or different measurement on its width, on its height, but have the similar shapes can be considered as distorted. Sixth is the simple form. If a crystal is bounded by all similar or like faces, it is called a simple form. If a crystal is bounded by dissimilar or unlike faces, it is called a combination. 7th, zone and zone axis. In many crystals, a group of faces are arranged in such a manner that their intersection edges are parallel to each other. Such faces constitute a zone, while a line passes through the center of the crystal and lie parallel to the line of the faces intersections is called the zone axis. 8. Crystallographic axis. In order to describe the faces and symmetry of crystal, a set of 3 or 4 reference axes are established. These imaginary reference lines are called crystallographic axes. While fixing a crystal in its study position with reference to the crystallographic axis, it is important to align it in such a way that one of the axes runs front to back from the observer, another runs right to the left, and one is passing from top to bottom of the crystal. Axial ratio. It is the ratio between the length of different crystallographic axes in a given crystal system. While unit cell is a tiny building block of crystal, each crystal is composed of number of such unit cells. In each unit cell, there is a group of atoms linked in a fixed spatial relationship to one another. 9th, symmetry. The faces, edges, and solid angles in crystals occur with some regularity. This is known as symmetry. Symmetry is property of fundamental importance for crystal. It can be studied with reference to 3 different characters, commonly called as elephants of symmetry, which are the plane of symmetry, the axis of symmetry, and the center of symmetry.
One of the scientific studies of mineralogy is the crystal structure of minerals. The minerals have characteristic of having regular internal structure. Thus, crystals, and therefore minerals, have an ordered internal arrangement of atoms. This arrangement of atoms shows symmetry. The concept of symmetry describes the periodic repetition of structural features.
In crystallography, there are terms called elements of symmetry. These elements are the plane of symmetry, axis of symmetry, and center of symmetry. The plane symmetry, often called a mirror plane, is an imaginary plane dividing a body into 2 parts such that each is the reflected image of the other. In crystals, it is possible to have more than one plane of symmetry. For example, a cube has 9 planes of symmetry, 3 of which are parallel to the surface and 6 are diagonals.
The second element is the axis of symmetry. It is an imaginary axis placed through a perfect crystal so that during a single rotation about the axis, the outline of the crystal form appears identically more than once, 2, 3, 4, or 6 times. Lastly, if an imaginary straight line can be passed through a crystal from any point on the surface of crystal such that the point of entry is similar to the point of exit, then the crystal has a center of symmetry. In order to identify the symmetry in a crystal or mineral, we have the so-called symmetry operations. These operations can be performed either physically or imaginatively that results no change in the appearance of an object. The 3 types of symmetry operations are rotation, reflection, and inversion. The rotation operations, both proper and improper, occur with respect to a line called rotation axis. There are 5 possible rotational symmetry in crystals. The first one is the one-fold rotation axis, where an object requires a rotation of full 360 degrees in order to restore to its original appearance. If an object appears identical after a rotation of 180 degrees, that is twice in a 360 degrees rotation, then it is said to have a two-fold rotation axis. The three-fold rotation axis happens if an object repeats itself upon rotation of 120 degrees. The four-fold rotation axis happens if an object repeats itself after 90 degrees of rotation. The last one is the six-fold rotation axis, where rotation of 60 degrees about an axis causes the object to repeat itself. Although objects may appear to have five-fold, seven-fold, eight-fold, or higher-fold rotation axes, these are not possible in crystals. The reason is that the external shape of a crystal is based on a geometric arrangement of atoms. Another symmetry operation is the reflection. It occurs when we put an object in front of a mirror. The image is found perpendicular to the reflection plane and equidistant from that plane. The resulting object can be distinguishable or indistinguishable from the original, normally distinguishable as they cannot be superimposed. If the resulting object is indistinguishable from the original, it is because the reflection plane is passing through the object. Another operation that can be performed is inversion through a point. In this operation, lines are drawn from all points on the object through a point in the center of the object, called a symmetry center. The lines each have lengths that are equidistant from the original points. When the ends of the lines are connected, the original object is reproduced inverted from its original appearance. There is also a term called roto-inversion operation, which is a combination of rotation with a center of symmetry. This operation is sometimes considered as the fourth operation in symmetry. Crystals are formed by the repetition in three dimensions of a unit cell structure defined by lattice points in space. There are only 32 ways to arrange the space lattices in terms of symmetry elements, and these are called the crystal classes. Thus, all crystals can be classified in 32 crystal symmetry classes according to their symmetry content. Each crystal class will have crystal faces that uniquely define the symmetry of the class. These faces or groups of faces are called crystal forms. These crystal forms constitute the crystal classes. Then the crystal classes constitute the 6 crystal systems. There are 6 crystal systems. All minerals form crystals in one of these 6 systems. Although we may have seen more than 6 shapes of crystals, they are all variations of one of these 6 habits. Each system is defined by a combination of 3 factors: how many axes it has, the length of the axis, and the angle at which the axes met. The 6 crystal systems include the isometric system, tetragonal system, hexagonal system, orthorhombic system, monoclinic system, and the triclinic crystal system. The isometric crystal system is also known as the cubic system. The crystallographic axes used in this system are of equal length and are mutually perpendicular, occurring at right angles to one another. All crystals of the isometric system possess 4 threefold axes of symmetry, each of which proceeds diagonally from corner to corner through the center of the cubic unit cell. Crystals of the isometric system may also demonstrate up to 3 separate fourfold axes of rotational symmetry. Furthermore, crystals of the isometric system may possess 6 twofold axes of symmetry. Minerals of this system may demonstrate up to 9 different mirror planes. There are 5 symmetry classes in an isometric system. These are the tetraedral, diploidal, gyroidal, hextetrahedral, and hexactahedral. Examples of isometric minerals are galena, pyrite, schellerite, spinel, magnetite, sodalite, garnet, diamond, fluorite, and leucite. The second crystal system is the tetragonal system. Minerals of the tetragonal crystal system are referred to three mutually perpendicular axes. The two horizontal axes are of equal length, while the vertical axis is of different length and may be either shorter or longer than the other two. Minerals of this system all possess a single fourfold symmetry axis. They may possess up to four twofold axes of rotation, a center or inversion, and up to 5 mirror planes. There are 7 symmetry classes in a tetragonal system. These are the tetragonal pyramidal, tetragonal dysphenoidal, tetragonal dyspyramidal, tetragonal trapezohedral, ditetragonal pyramidal, tetragonal scalenohedral, and ditetragonal dipyramidal. Examples of tetragonal minerals are zircon, vesuvianite, rutile, wernerite, cassiterite, octahedrite, chalcopyrite, scheelite, wolfenite, and brownite. The third crystal system is the hexagonal system. Minerals of the hexagonal crystal system are referred to the crystallographic axes which intersect at 120 degrees and a fourth which is perpendicular to the other three. This fourth axis is usually depicted vertically. The hexagonal crystal system is divided into the hexagonal and rhombohedral or trigonal divisions. All crystals of the hexagonal division possess a single six-fold axis of rotation. They may also possess up to 6 two-fold axes of rotation. They may demonstrate a center of inversion symmetry and up to 7 mirror planes. Crystals of the trigonal division all possess a single three-fold axis of rotation. Crystals of this division may possess up to 3 two-fold axis of rotation and may demonstrate a center of inversion and up to 3 mirror planes. There are 12 symmetry classes in a horizontal system. These are the trigonal pyramidal, rhombohedral, trigonal trapezohedral, ditrigonal pyramidal, hexagonal scalenohedral, hexagonal pyramidal, trigonal dipyramidal, hexagonal dipyramidal, hexagonal trapezohedral, dihexagonal pyramidal, ditrigonal dipyramidal, and dihexagonal dipyramidal. Examples of hexagonal minerals are quartz, corundum, tourmaline, calcite, beryl, hematite, brucite, concrenite, willemite, and chabazite. The fourth crystal system is the orthorhombic system. Minerals of the orthorhombic crystal system are referred to three mutually perpendicular axes, each of which is of a different length than the others. Crystals of this system uniformly possess 3 two-fold rotation axes and or 3 mirror planes, as well as a center of inversion. Other classes may demonstrate 3 two-fold axes of rotation or 1 two-fold rotation axis and 2 mirror planes. There are 3 symmetry classes in an orthorhombic system. These are the rhombic dysphenoidal, rhombic pyramidal, and rhombic dipyramidal. Examples of orthorhombic minerals are sulfur, staurolite, andalusite, topaz, barytes, aragonite, enstatite, antophyllite, stibnite, and calamine. The fifth crystal system is the monoclinic system. Crystals of the monoclinic system are referred to 3 unequal axes. 2 of these axes are inclined toward each other at an oblique angle. These are usually depicted vertically. The third axis is perpendicular to the other 2. The 2 vertical axes therefore do not intersect one another at right angles. Monoclinic crystals demonstrate a single two-fold rotation axis and or a single mirror plane. There are 3 symmetry classes in a monoclinic system. These are the sphenoidal, dematic, and prismatic. Examples of monoclinic minerals are gypsum, orthoclase, and pyroxene. The last crystal system is the triclinic system. Crystals of the triclinic system are referred to 3 unequal axes, all of which intersect at oblique angles. None of the axes are perpendicular to any other axis. Crystals of the triclinic system may be said to possess only a one-fold symmetry axis, which is equivalent to possessing no symmetry at all. Crystals of this system possess no mirror planes. There are only two symmetry classes in a triclinic system. These are the pedial and pinacoidal. Examples of triclinic minerals are albite, kyanite, axonite, microcline, anorthite, rhodonite, and turquoise. Again, the 32 symmetry classes are divided into 6 crystal systems, 5 in isometric system, 7 in tetragonal system, 12 in the hexagonal system, 3 in the orthorhombic system, 3 in the monoclinic system, and 2 in the triclinic system, and based from the symmetry elements like for the fold symmetry in the graph, the symmetry from isometric system to triclinic system decreases.
Let's talk about the study of the rock-forming minerals. Rocks are composed of minerals. A mineral is a naturally occurring substance which is usually solid, crystalline, stable at room temperature, and inorganic. There are almost 5,000 known mineral species, yet the vast majority of rocks are formed from the combinations of the few common minerals, referred to as rock-forming minerals. The rock-forming minerals are feldspar, quartz, amphiboles, micas, olivine, garnet, calcite, and pyroxenes.
Minerals occurring within a rock in small quantities are referred to as accessory minerals. Although accessory minerals are present in only small amounts, they may provide valuable insight into a geological history of a rock, and are often used to ascertain the age of a rock. Common accessory minerals are zircon, monazite, apatite, titanite, tourmaline, pyrite, and other opaques. The abundance and diversity of minerals depend on the abundance in the earth crust of the elements of which they are composed. So there are 8 elements that make up the 98% of the earth's crust. So these are the oxygen, silicon, aluminum, iron, magnesium, calcium, sodium, and potassium. By igneous processes, the composition of minerals can be formed, and it is directly controlled by the chemistry of the parent body. For example, a magma rich in iron and magnesium will form minerals such as olivine and pyroxene, as found in basalt. The magma richer in silicon will form more silica-rich minerals such as feldspar and quartz, as found in granite. It is unlikely that a mineral will be found in a rock with dissimilar bulk chemistry unlike its own. Thus, it is unlikely that andesite would be found in an aluminum-poor rock such as quartzite. To be considered a common rock-forming mineral, a mineral must be one of the most abundant minerals in Earth's crust, and be one of the original minerals present at the time of the crystal rock's formation, and be an important mineral in determining rock's classification. Minerals that easily meet these criteria include plagioclase, feldspars, alkali feldspars, quartz, pyroxenes, amphiboles, micas, clays, olivine, calcite, and dolomite. In major rock types, in rock-forming minerals, this chart shows the relative abundance of the common rock-forming minerals in some of the Earth's most abundant rock types. Basalt and gabbro count for most of the rock in the oceanic crust, while granite and andesite represent the abundant rock types of the continental crust. Sandstone, shale, and carbonate represent the common material in the sedimentary cover of continents and ocean basins. Minerals of the oceanic crust. As an example of the influence of just few minerals, let's consider the rocks of the oceanic crust. The oceanic crust is mainly composed of basalt and gabbro. These two rock types are made up of mainly plagioclase, feldspar, and pyroxenes, with smaller amount of olivine, micas, and amphiboles. This small group of minerals make up most of rocks of the oceanic crust. Minerals of the continental crust. As a second example, let's consider the rocks of the continental crust. The continental crust is made up mainly of rocks with a granitic to andesitic composition. These rocks are composed of mainly of alkali feldspar, quartz, and plagioclase feldspar, with smaller amount of amphiboles and micas. This small number of minerals makes up most of the continental crust. Minerals in sedimentary cover. Both the oceanic and continental crust are partly covered with a thin layer of sedimentary rocks and sediments. These consist mainly of clastic rocks such as sandstone, siltstone, and shale, along with carbonate rocks such as dullstone and limestone. These clastic rocks are composed of mainly quartz, clay minerals, and a small amount of micas and feldspar minerals. The carbonate rocks consist primarily of calcite and dolomite. A small number of materials composed of a small number of minerals make up most of the sediment and sedimentary rocks that cover the continents and ocean basins. Rock-forming mineral. Any mineral that forms igneous, sedimentary, or metamorphic rocks and that typically or solely forms as an intimate part of rock-making processes. In contrast, are those minerals that have a limited mode of occurrence or are formed by more unusual processes, such as the ores of metals, vein minerals, and cavity fillings. Also, some precipitates and secondary minerals are not properly classified as rock-forming minerals. These form at a later time than original rock and tend to destroy its original character. Some mineralogists limit the rock-forming minerals to those that are abundant in rock and that are usually called essential minerals, a definition implying that they are those most significant in studying rock-making processes.
Most minerals can be characterized and classified by their unique physical properties. And mineralogists use this to help them determine the identity of a specimen. Here are the 12 physical properties of minerals: color, strength, hardness, cleavage or fracture, crystalline structure, their finity, tenacity, magnetism, luster, odor, taste, and specific gravity.
Color. Most minerals have a distinctive color that can be used for identification. In opaque minerals, the color tends to be more consistent, so learning the colors associated with these minerals can be very helpful in identification. Translucent to transparent minerals have much more varied degree of color due to the presence of trace minerals. Therefore, color alone is not reliable as a single identifying characteristic. Streak. Streak is the color of the mineral in powdered form. Streak shows the true color of the mineral. In large solid form, trace minerals can be changed the color appearance of a mineral by reflecting the light in a certain way. Trace minerals have little influence on the reflection of the small powdery particles of the streak. Hardness. Hardness is one of the better properties of minerals to use for identifying a mineral. Hardness is a measure of the mineral's resistance to scratching. The Mohs scale is a set of 10 minerals whose hardness is known. The soapest mineral, talc, has a Mohs scale rating of 1. Diamond is the hardest mineral and has rating of 10. Sulfur minerals can be scratched by harder minerals because the forces that holds the crystal together are weaker and can be broken by the harder mineral. The following is a listing of the minerals of the Mohs scale and their rating: talc, gypsum, calcite, fluorite, apatite, orthoclase, feldspar, quartz, topaz, corundum, and diamond. Cleavage and fracture. Minerals tend to break along lines or smooth surfaces when hit sharply. Different minerals break in different ways, showing different types of cleavage. Fracture describes the quality of the cleavage surface. Most minerals display either an even or grainy fracture. Conchoidal, curved shell-like lines, fracture, or Hackley,
rough jagged fracture. Crystalline structure. Mineral crystals occurs in various shapes and sizes. The particular shape is determined by the arrangement of the atoms, molecules, or ions that make up the crystals and how they are joined. This is called the crystal lattice. Transparency or diaphanity. Diaphanity is a mineral's degree of transparency or ability to allow light to pass through it. The degree of transparency may also depend on the thickness of the mineral. To test for transparency, hold the specimen up to the light. If you can see through it, is called transparent. If you put your finger behind the mineral and can see the shadow of your finger, it is called translucent. If no light comes through it, is called opaque. Tenacity. Tenacity is the characteristic that describes how the particles of a mineral hold together or resist separation. Magnetism. Magnetism is the characteristic that allows a mineral to attract or repel other magnetic materials. It can be difficult to determine the differences between the various types of magnetism, but it is worth knowing that there are distinctions made. Luster. Luster is the property of minerals that indicates how much the surface of a mineral reflects light. The luster of a mineral is affected by the brilliance of the light used to observe the mineral surface. Luster of a mineral is described in the following terms. First is metallic. The mineral is opaque and reflects light as a metal would. Submetallic. The mineral is opaque and dull. The mineral is dark colored. Non-metallic. The mineral does not reflect light like a metal. Odor. Most minerals have no odor unless they are acted upon in one of the following ways: moistened, heated, breathed upon, or rubbed. Taste. Only soluble minerals have a taste, but it is very important that minerals not be placed in the mouth or on the tongue. You should not test for this property in the classroom. Now, let's move on to the last but not the least physical properties of minerals. Specific gravity. The specific gravity of a mineral is a comparison or ratio of the weight of the mineral to the weight of an equal amount of water. The weight of the equal amount of water is found by finding the difference between the weight of the mineral in the air and the weight of the mineral in the water.
Minerals are formed in all geologic environment and thus under a wide range of chemical and physical conditions such as varying temperature and pressure.
Igneous or magmatic, in which minerals crystallize from a melt. Sedimentary, in which minerals are the result of sedimentation, a process whose raw materials are particles from other rocks that have undergone weathering or erosion. Metamorphic, in which new materials form at the expense of earlier ones owing to the effect of changing, usually increasing temperature or pressure, or both on some existing rock type. And hydrothermal, in which minerals are chemically precipitated from hot solution within Earth. These are the four main categories of mineral formation. But, how are minerals even formed? Keep in mind that all minerals are found within rocks, so many minerals are formed when these rocks are formed. Minerals can be formed in few main ways: deposition from volcanic gases, crystallization of lava and magma, and evaporation from aqueous solutions. Deposition is the process of going from a gas directly to a solid. When volcanoes erupt, lots of gases are released. The contrast between the temperature of the extreme hot volcano and much cooler atmosphere means that some of those gases form lower energy solids pretty quickly without even passing the liquid phase. Cooling of magma or lava results in crystals and igneous rocks being formed. Through the Bowen's reaction series, different minerals are formed at different temperatures of this cooling process. Another way they can form is after hot water flows between rocks and dissolved particles. When this water cools, these dissolved particles return to a solid state deposit or precipitate back out. Evaporation can also lead to minerals being formed. if a seawater has a large salt content and that seawater evaporate, it can leave behind those minerals as they settle to the bottom. Example of mineral formed in this process is a rock gypsum. Now, some minerals won't always remain the same mineral. A mineral can change form or morph and be replaced by another mineral based on environmental condition. In general, it's just one mineral replaced by another because of a change to its chemical composition. These gradual replacement lead to some pretty cool-looking samples called pseudomorphs, meaning false form. These samples usually have some of both minerals present. One famous example of a pseudomorph is the malachite-azurite combo. Malachite slowly replaced the azurite by losing its hydroxyls in a chemical change. Pseudomorphs aren't to be confused with polymorphs, which are minerals with the same chemical formula but different atomic arrangement. The most commonly example of these is graphite and diamond, since they are made of pure carbon but the different arrangement lead to their different properties. Graphite is more slippery since it's arranged in sheets, while diamonds is stronger because of its tetrahedral form. There's one more important thing to discuss about mineral formation. Since minerals form from crystallization, sometimes crystals can grow abnormally. Error in a mineral growth because of environmental condition can result in twinning. Twinning is the symmetrical growth of two crystals from similar lattice points. The way a mineral twin can help to identify it since different minerals have different twinning patterns. There are two main types of twinning: contact and penetration. Contact twins involve twin crystals sharing only one plane between them, looking just like touching each other, while penetration twins involve one of the crystals going through the other one. In other words, more than one plane is shared.
Thank you, Alexis, for that very informative discussion of yours. And now, let's move to the next chapter of studying mineralogy. Let's talk about quartz family, feldspar family, agites, and hornblende. Also, the biotite, muscovite, calcite, and garnet, which are all essential in almost every aspect of our lives and even extend to the deepest foundation of civil engineering. I am Kenneth Nefiles. Join me as we unveil the narrative of this group of minerals.
Lesson 5: Understanding Quartz Family, Feldspar Family, Agite, Hornblende, Biotite, Muscovite, Calcite, and Garnet. Quartz Family. Quartz is a chemical compound consisting of 1 part silicon and 2 parts oxygen, or simply called the silicon dioxide. Quartz has 3 main varieties. First is the crystalline quartz, that refers to those quartz who have an obvious crystals and can easily seen by a naked eye. The gemstone included with this type of quartz are namely amethyst, rock crystal, rosy quartz, and milky quartz. Second variety is the cryptocrystalline, or minerals of rocks composed of crystals that can be distinguished individually only by the use of polarizing microscope. Examples are chalcedony, carnelian, chrysoprase, heliotrope, agate, flintstone, and jasper. And for the third, the amorphous or non-crystalline quartz. One notable example is the opal. Now, it's time for the big trivia. Did you know that the name quartz may be derived from the word Quercluf earth, an old German word referring to whitish vein quartz, or from the ancient Greek word krustallus, meaning ice, because the Greeks and the Romans believed that quartz was an ice that never melted because it was formed by the gods. Second trivia. Quartz are the most mineral found at Earth's surface since it was made of the 2 most abundant chemical elements on Earth, the oxygen and the silicon. It forms at all temperature. Fourth, it is highly resistant to both mechanical and chemical weathering. And fifth, quartz is ubiquitous, plentiful, and durable. Quartz is one of the most useful natural materials. Its usefulness can be linked to its physical and chemical properties. So, let's talk about the properties. Its chemical composition falls under the silicate group. In terms of color, quartz often appeared in every color. However, the common colors of it includes gray, clear, white, purple, yellow, brown, black, pink, green, and red. Quartz are colorless. They are harder than a streak plate. On the other side, quartz has a vitreous or glassy luster. The affinity obviously transparent to translucent. Quartz is typically breaks with a conchoidal fracture, meaning it has mostly no cleavage. Quartz has a scale of 7 from most hardness table, meaning it is incredibly hard and unscratchable. The specific gravity ranges from 2.6 to 2.7. However, the diagnostic properties of quartz are conchoidal fracture, glassy luster, hardness. Lastly, quartz has a hexagonal crystal system. Another notable property of quartz is that the quartz crystal have these piezoelectric properties and heat resistance make quartz valuable in electronic products. Lastly, according to Emily Rectis, there are a number of different types of quartz crystals that has their own healing ability for the mind, body, and soul. Some examples are clear quartz, rose quartz, jasper, and obsidian. This indicates that quartz is all-inclusive and all-essential. Now, let's talk about the occurrence. Quartz and its varieties occur in all types of rocks: igneous, sedimentary, and metamorphic. This makes sense knowing quartz is ubiquitous. In igneous rocks, quartz makes us bulk of acidic varieties. In sedimentary rocks, quartz makes us soundstone and orthoquartzite. Also, the loose sand consists mostly of quartz grain, while the metamorphic rocks like gneisses contain good proportion of quartz in some cases. Other one, a metamorphic rock named Para quartzite is entirely made up of quartz. What are the uses of quartz? Use in glass making. Quartz has those deposit that produce a high purity silica sand. These sands are used in a glass making industry. Quartz sand is used in the production of container glass, flat plate glass, specialty glass, and fiber. Uses of quartz as an abrasive. The high hardness of quartz, 7 on the Mohs scales, makes it harder than most other natural substances. As such, it is an excellent abrasive material. Quartz sand and finely ground silica sand are used for sandblasting, scoring cleanser, grinding media, and grit for sanding and sewing. Uses of quartz as a foundry sand of metals or quartz sand. Quartz is a very resistant to both chemicals and heat. It is therefore often used as a foundry sand. With a melting temperature higher than most metals, it can be used for the molds and cores of common foundry work. Uses in the petroleum industry. Quartz sand has a high resistance to being crushed. In the petroleum industry, sand slurries and forced down oil and gas wells under very high pressure in a process known as hydraulic fracturing. This high pressure fractures the reservoir rocks, and the sandy slurries injects into the fractures. The durable sand grains hold the fracture open after the pressure is released. This open fracture facilitates the flow of natural gas into the well bore. Many other quartz sand uses filler in the manufacture of rubber, paint, and putty, abstraction in the railroad and mining industries. Quartz is also used for quartz crystal and makes an excellent gemstone. Today, billions of quartz crystals are used to make oscillators for watches, clocks, radios, television, electronic games, computer, cell phones, electronic meters, and the GPS equipment. The relevance of quartz in engineering. It is important to note that if quartz, sand, and gravel are to use as a building material, it is necessary to carry out the analysis thoroughly. It is due to its varying properties that can affect some aspect of building materials of your house. Second, when the quartz and its species used as aggregates in cement start to harden with high alkali cement, hydro treatment occurs on sodium, potassium, etc. The alkalis are released. All silicates, especially opal, chalcedony, and agate, and siliceous minerals act with alkalis, causing the concrete material to expand, crack, break down, and eventually reduce its strength. Therefore, 7 cement aggregate reaction become important according to the size and importance of the structure to be constructed.
Feldspar family. Feldspar is the name given to the group of minerals distinguished by the presence of alumina and silica in their chemistry. This group includes aluminum silicates of soda, potassium, or lime. The two types of feldspar, alkali and the plagioclase. Plagioclase, group of feldspar mineral that form a solid solution series ranging from pure albite to pure anorthite. Each plagioclase grain is made up of stack of thin crystal with their molecules arranged in opposite directions. This causes the cleavage planes to have fine parallel lines across them called striations. Examples of plagioclase are albite, oligoclase, labradorite, spectrolite, lunar plagioclase. The second type is the alkali feldspar. Alkali feldspar is a feldspar mineral with a chemical composition of KAlSi3O8. Unlike plagioclase, alkali feldspar does not have striations across its cleavage plane. Cleavage pieces will appear smooth. Did you know? Many geologists call autoclase K-spar or K-feldspar or potassium feldspar because autoclase is rich in potassium in an end member of the alkali feldspar series. Example of alkali are pink granite, colored moonstone. The general property of feldspar: class classification, silicate, color usually white, pink, gray, or brown. Also, colorless yellow, orange, red, black, blue, and green. Streak is white, luster is vitreous, barely on warm cleavage bases. Diaphanity usually translucent to opaque. Relief transparent. Cleavage is perfect in two directions. Cleavage planes usually intersect at a close to a 90-degree angle. Most hardness is 6 to 6.5. Specific gravity is 2.5 to 2.8. Diagnostic properties: perfect cleavage with a cleavage bases usually intersecting at or close to a 90 degrees. Consistent hardness, specific gravity, and fairly luster on. Chemical composition is a generalized chemical composition of XAlSi4O8, where X is usually potassium, rubidium, or strontium. The crystal system of feldspar is triclinic and monoclinic. Although there are many feldspar minerals that all share a tight range of physical properties that are surprisingly consistent.
Here for the properties of feldspar. Plagioclase versus alkali. We can see that there is no much differences between the two feldspar except in terms of chemical composition and crystal system. Occurrence. Plagioclase are abundant in all types of igneous rocks except the ultra-basic rocks in basic and intermediate lavas. Plagioclase, phenocryst, as well as small grain in the ground mass are abundant and exhibit zoning. Alkali feldspar are restricted to alkali and acid igneous such as cyanite, granite, metamorphic gneisses, and less frequently in sedimentary rocks like arkose. Uses of feldspar. Some uses of the feldspar family is generally include glassware, pottery, scoring solution, fillers, paint, plastic, rubbers. Semi-precious gemstone. Feldspar family members are widely used in jewelry industry. They provide a great choice of natural colors. They come in a large sizes. They provide beautiful optical effects. The feldspar are often described as having a silular, opalescence, or adorescence. These terms all refer to the shimmering effect that appears to sit just below or above the surface of the stone when it is placed or moved under a light. Moonstone is well known for this special optical effect in which reflected light causes a blue or white scalar, and building and monuments. Feldspar in engineering. Feldspar are used as fluxing agent to form glassy paste at low temperature and as a source of alkalis and alumina in glazes. This improve the strength, toughness, and durability of the ceramic body and cement the crystalline paste of other ingredients, softening, melting, and wetting other batch constituents. Agate. Agate is a rock-forming mineral of the pyroxene group, commonly found within the igneous as a basalt, gabbro, andesite, and dorite, and metamorphic rocks. Agate has a chemical composition of calcium, sodium, magnesium, iron, aluminum, silicon, aluminum, 2O6, with many solid solutions. Agate is the most common pyroxene mineral and a member of clinopyroxene group. Some people use the name agate and pyroxene interchangeably, but this usage is strongly discouraged. There are a large number of pyroxene minerals, many of which are distinctly different and easy to identify. Agate is usually green, black, or brown in color, with a translucent to opaque affinity. It usually inhibits two distinct cleavage directions that intersect at slightly less than 90 degrees. A hand lens is often needed to properly observe the cleavage, especially in a fine-grained rocks. Light reflecting from cleavage surfaces and crystal bases of agate produces a vitreous luster, while light striking other surfaces produces a dull luster. Agate has a most hardness of 5.5 to 6. Its specific gravity of 3.2 to 3.6 is higher than most other minerals in the rocks in which it occurs. For the other properties, you can refer to the table. Occurrence. Agate occurs in gabbro, basalt, mafic igneous rocks, metamorphosed iron formation, ultramafic rocks, and some high-graded metamorphic rocks. It is closely associated with minerals like pyroxenes, amphiboles, lyocite, olivine, labradorite, sanidine, and orthoclase. Uses of agate. Agate does not have any physical, optical, or chemical properties that make it especially useful. It is therefore one of the few minerals that has no commercial use. The calcium content of agate has been found to be limited use in
studies of the temperature history of igneous rocks. However, some notable uses of it are in ceramics, ceramic glazing, manufacturing aluminum, and in purifying water. Hornblende. Hornblende is a field and classroom name used for a group of dark-colored amphibole minerals found in many types of igneous and metamorphic rocks. These minerals vary in a chemical composition but are all double-chain insilicates with very similar physical properties. Generalized composition for hornblende CaNa2-3 MgFeAl5 SiAl8O222 OHF2. Note: the calcium, sodium, magnesium, iron, aluminum, silicon, fluorine, and hydrocell can all vary in abundance. Trivia alert. Name: the word is derived from the German horn and blende, which means to distill. It is allusion to its similarity and appearance to a metal-bearing ore minerals. The physical properties of hornblende. Its chemical classification falls under the silicate group. The color is usually black, dark green, dark black. Its streak is white, colorless. It is also brittle, often leaves cleavage debris behind instead of a streak. The same with quartz. It has a vitreous glassy luster, translucent to nearly opaque for diaphanity. The cleavage has two directions intersecting at 124 and 56 degrees. According to most Hardy scale, it ranges from 5 to 6. The specific gravity is 2.9 to 3.5, varies depending upon the composition. The diagnostic properties are cleavage, color, elongated habit. The crystal system is monoclinic. Types of hornblende. There are two types of hornblende, namely the ferrohornblende and the magnetio-hornblende. Some examples are shown in this slide. Occurrence. It is a common component of many magmatic and metamorphic rocks such as granite, diorite, gabbro, basalt, andesite, gneiss, and schist. It is the main mineral of amphibolites. Adenite, a rare kind of hornblende, contains less than 5% of iron oxide. Uses of hornblende. The mineral hornblende has very few uses. Its primary use might be as a mineral specimen. However, hornblende is the most abundant mineral in a rock known as amphibolite, which has a large number of uses. It is crushed and used for highway construction and as a railroad ballast. It is cut for use as a dimension stone. The highest quality pieces are cut, polished, and sold under the name black granite for use as a building facing, floor tiles, countertops, and other architectural uses. Hornblende has been used to estimate the depth of crystallization of plutonic rocks. Those with low aluminum content and are associated with shallow depths of crystallizations, while those with higher aluminum content are associated with greater depths of crystallization. This information is useful in understanding the crystallization of magma and also useful for mineral exploration. Its primary use might be as a mineral specimen. Biotite. Biotite is a name used for a large group of black mica, minerals that are commonly found in an igneous and metamorphic rock. The generalized composition for biotite group is KMgFe3, AlSi3O10, FOH2. The name biotite is used in the field and in interlevel geology courses because these minerals generally cannot be distinguished without optical, chemical, or X-ray analysis. Biotite minerals include annite, phlogophyte, siderolophyte, fluoroglophite, fluoroannite, estonite, and many others. The chemical composition for these were shown in the table. The properties of biotite. Biotite is very easy to identify, and with a large experience, a person will be able to recognize it on sight. It is a black mica with perfect cleavage and a vitreous luster on the cleavage faces. When biotite is separated into its sheets, the sheets are flexible but will break upon severe bending. When held up to the light, the sheets are transparent to translucent with a brown, gray, or greenish color. Experienced observer can sometimes recognize plausible by its brown color. For further properties of biotite, please refer to the table presented. Occurrence or range of biotite. From this point of presentation, we can see that biotite is a rock-forming mineral found in a wide range of crystalline igneous rocks, metamorphic rocks, and sedimentary rocks. Granite, diorite, gabbro, peridotite, and pegmatite belong to the igneous biotite. For metamorphic, gneiss and biotite seas, and opal for sedimentary rocks. The uses of biotite. Biotite has a small number of commercial uses. Ground mica is used as a filler and extender in paints and as additive to drilling muds, as an inert filler and mold release agent in rubber products, and as a non-stick surface coating on the asphalt, shingles, and road roofing. It is also used in the potassium argon and argon methods of dating igneous rocks. The other uses of biotite is that it is classified as the other post-gold. A few tiny flakes of biotite swishing in a gold pan can produce a bright brown colored reflection in the pan, which struck by the sunlight. This reflection can fool the inexperienced panner into thinking that he has found gold. Muscovite. Muscovite is the most common mineral of the mica family. It is an important rock-forming mineral present in an igneous, metamorphic, and sedimentary rocks. Like other micas, it readily cleaves into thin transparent sheets. Muscovite sheets have a fairly to vitreous luster on their surface. If they held up to the light, they are transparent and nearly colorless, but most have a slight brown, yellow, green, or rose colored tint. The chemical composition of muscovite. Muscovite is a potassium-rich mica that has a generalized composition of KAl2, AlSi3O10, OH2. In this formula, potassium is sometimes replaced by other ions with a single positive charge as sodium, rubidium, or potassium. Aluminum is sometimes replaced by magnesium, iron, lithium, chromium, or vanadium. The properties of muscovite. Muscovite is easily identified because its perfect cleavage allows it to be split into thin, flexible, elastic, colorless, transparent sheets with a fairly to vitreous luster. It is only common mineral with these properties. The other properties are shown in the table. These properties include muscovite's chemical classification, color, strike, luster, diaphanity, cleavage, most hardness, specific gravity, diagnostic properties, chemical composition, and crystal system. Occurrence. Muscovite is found in an igneous, metamorphic, and sedimentary rocks. In igneous rocks, it is a primary mineral that is especially common in granitic rocks. Muscovite can occur also as isolated grains in seas and gneiss, or it can be abundant enough that the rocks are called mica seas or micaeous gneiss. The uses of muscovite. Muscovite can be used as windows on high-temperature furnaces and oven due to its high resistance to heat and can split into thin transparent sheets. Muscovite is an insulator and was used in the past to make circuit boards. It was also used as an early window glass, historically speaking. The ground mica, mostly muscovite, is used to manufacture a variety of products such as paint, drilling, muds, plastics, rubber, asphalt, roofing, and cosmetics. However, sheet mica is used to make electronic devices such as oxygen drilling equipment, Merkel dials for navigation compassers, optical pillars, pyrometers, retardation plates, missile system components, radar systems, radiation detector windows, and calibrated capacitors. Calcite. Calcite is a rock-forming mineral with a chemical formula of CaCO3. It is extremely common and found throughout the world in sedimentary, metamorphic, and igneous rock. Some geologists consider it to be a ubiquitous mineral. The properties of calcite. Calcite belongs to the carbonate group as a chemical classification. It is usually white but also colorless gray, red, green, blue, yellow, brown, or orange in color. It has white streak and vitreous luster. It is considered as transparent to translucent as calcite affinity. The cleavage of it is perfect, rhombohedral, and has 3 directions. However, it is soft mineral since it has only 3 points in most hardness scale. 2.7 is the specific gravity, and the crystal system is seen as hexagonal. Occurrence. Calcite occurs in major rock-forming minerals, in limestone, marbles, and chalks. A common cement in Chester sedimentary rocks as a gangue in hydrothermal mines, in alkali to mafic igneous rocks, and commonly as speleothems in caves. For the uses of calcite, let's start with the calcite as limestone and marble. Limestone is a sedimentary rock that is composed primarily of calcite. It forms from both the chemical precipitation of calcium carbonate and the transformation of shell, coral, fecal, and algae debris in calcite during diagenesis, or the process that describes the physical and chemical changes in sediments first caused by the water-rock interaction, microbial activity, and compaction after their deposition. In terms of marble, the marble is a metamorphic rock that forms when limestone is subjected to heat and pressure. A close examination of broken piece of marble will usually reveal obvious cleavage spaces of calcite. Other uses of calcite. Acid neutralization. For hundreds of years, limestone and marbles have been crushed and spread on fields as an acid neutralizing soil treatment. In the chemical industry, calcite is used as a low hardness abrasive, soil conditioner, or haled for the production of lime. Calcite helps also to remove carbon dioxide from the atmosphere and store it away from long period of time through a formation of limestone, whereas it also helps to develop the tourism of a specific place. Calcite in engineering and construction. The production of marble blocks for monuments and statuary is basically from calcite. Calcite in concrete used also in a high-rise building, where in fact the calcite in the form of limestone is used to make cement and also used as the aggregate in the most concrete. Garnet. Garnet is the name used for a large group of rock-forming minerals. These minerals share a common crystal structure and generalized chemical composition of X3Y2 SiO4 3. In that composition, X can be a calcium, magnesium, Fe2+, or Mn2+, and Y can be aluminum, Fe3+, Mn3+, B3+, or Cr3+. Most people associated the word garnet with a red gemstone. However, they are often surprised to learn that garnet occurs in many other colors and has many other uses. Pan-historical Park. In 2012, the USA has recorded the major industrial uses of garnet, found to be water jet cutting 35%, abrasive blasting media 30%, water filtration granules 20%, and abrasive powders 10%. Properties of garnets. The most commonly encountered minerals in the garnet group include almadine, pyrroof, and uvarovite. They have a vitreous luster, a transparent to translucent diaphanity, a brittle tenacy, and a lack of cleavage. However, the wide variation in chemistry determines many of their physical properties. As an example, the calcium garnets generally have a lower specific gravity, a lower hardness, and are typically green in color. In contrast, the iron and manganese garnets have a higher specific gravity and a greater hardness and the typical red in color. Occurrence. The rock-forming garnets are most common in metamorphic rocks. Few occur in igneous rocks, especially granite and granitic pegmatites. Garnet derived from some rocks occur sporadically in clastic sediment and sedimentary rocks. For the typical occurrences of some garnet minerals, please refer to this table, wherein the garnets include the formerly mentioned garnets. The uses of garnets. Garnet is used as an industrial mineral, particularly as abrasive. It also used as a sandpaper, wherein it performs excellent. Garnet has crystal, making it essential in crystal production. Other uses of garnets are infiltration, geological indication, and as gemstones.
The last two lessons are about some exhaustible natural resources such as coal and petroleum. Coal and petroleum were formed by the decomposition of vegetation under heat and pressure. Both are fuels and supplies energy. In this lesson, we will discuss what is coal and what is petroleum. Coal and petroleum are both abundant fossil fuels that supplies energy. They are useful for industrial and domestic purposes. When burnt, coal and petroleum emits harmful gases during the process of combustion. Coal. Coal is a black-colored combustible rock containing more than 50% by weight of carbon. It is formed depending on the amount of oxygen, carbon, and hydrogen they contain. Carbon is one of the most important fossil fuels that is used to generate electricity. The process of formation of coal is called carbonization, and the time period during this process is called Carboniferous age. Carbonization is the conversion of organic matters like plants and dead animal remains into carbon through destructive distillation. Coal is taken out from the earth by the process of underground mining or surface mining. Underground mining is used to extract ore from the surface of the earth safely. The entry from the surface to an underground mine may be through a horizontal or vertical tunnel known as shaft or decline. Surface mining is a form of mining in which the soil and the rock covering the mineral deposits are removed. It is the other way of underground mining in which the overlying rock is left behind, and the required mineral deposits are removed through shafts or tunnel. Coal can be divided into four classes: anthracite, bituminous, subbituminous, and lignite. Anthracite coal is a dense, hard rock with a jet black color and a metallic luster. It contains between 86% and 98% carbon by weight, and it burns slowly with a pale blue flame and a very little smoke. Bituminous coal or soft coal contains between 69% and 86% carbon by weight and is the most abundant form of coal. Subbituminous coal contains less carbon and more water, and is therefore a less efficient source of heat. Lastly, lignite coal or brown coal is a very soft coal that contains
up to 70% water by weight. Coal is used for domestic and industrial purposes. When coal is processed in the industry, it produces some useful products such as coke, coal tar, and coal gas. Coke is a hard, porous, and a black substance in the almost pure form of carbon. Coke is usually used in manufacturing steel and in the extraction of many metals. Coal tar is described as a black, thick liquid and has an unpleasant smell. Products obtained from coal tar are used as starting materials for manufacturing various substances used in everyday life and in the industry such as paints, roofing materials, synthetic dyes, explosives, drugs, perfumes, plastics, and photographic materials. Bitumen products obtained from petroleum products is used in place of coal tar for metalling the roads. Coal gas is a gaseous mixture, mainly hydrogen, methane, and carbon monoxide, formed by the destructive distillation of bituminous coal and used as a fuel. Petroleum. Petroleum is a black-colored, oily liquid fossil fuel which has an unpleasant odor, is composed of a variety of hydrocarbons. The word petroleum is derived from the word petra, which means rock, and oleum, which means oil, as it is mined between the rocks under earth. Petroleum was formed from organisms living in the sea, created by the decomposition of organic matter beneath the surface of the earth millions of years ago. Petroleum is found in underground pockets called reservoirs. Deep beneath the earth, the pressure is extremely high. Petroleum slowly seeps out toward the surface where there is a lower pressure. It continues this movement from high to low pressure until it encounters a layer of rock that is dense. When petroleum is first collected in its natural form, it is called crude oil. By the process called fractional distillation, crude oil is refined where different hydrocarbons separate to form different fractions. This is later refined to usable substance such as petrol, kerosene, paraffin, diesel, and lubricating oil. There are two common forms of petroleum. One is natural gas, the other is crude oil. Natural gas is a mixture of lightweight alkanes. A typical sample of natural gas when it is collected at its source contains 80% of methane, 70% of ethane, 6% of propane, 4% of butane and isobutane, and 3% of pentanes. The propane and butanes removed from natural gas are usually liquefied under pressure and sold as liquefied petroleum gases. Crude oil is a complex mixture that is between 50 and 95% hydrocarbon by weight. The first step in refining crude oil involves separating the oil into different hydrocarbon fractions by distillation. About 10% of the product of the distillation of crude oil is a fraction known as straight-run gasoline, which served as a satisfactory fuel during the early days of the internal combustion engine. Petroleum products are yielded from the refinement of crude oil in oil refineries. Refining petroleum obtains usable constituents or substances such as liquid petroleum gas, petrol, kerosene, diesel, lubricating oil, paraffin wax, and bitumen.
And now let us discuss about the origin and occurrence of coal and petroleum.
It is generally accepted that coal originated from plant debris including ferns, trees, bark, leaves, roots, and seeds, some of which accumulated and settled in swamps. This unconsolidated accumulation of plant remains is called peat. Peat is being formed today in marshes and bogs. Layers of peat covered by sediment receiving heat and pressure from subsidence of the swamp went through metamorphic process called qualification to form coal. The metamorphic process is thought to have occurred in several stages. The conditions of the metamorphic process of the swamp and bogs greatly affected the formation of the coal. Several factors which greatly affected the content, makeup, quality, and rank of coal were temperature, pressure, time, layering process, fresh water, seawater, swamp acidity, types of plant debris, types of sediment cover. Coal is first formed from peat, has high moisture content and relatively low heating value. Coal rank. Coal is usually divided into two main classes, anthracite or hard coal and bituminous soft coal. When anthracite was formed, it was squeezed in greater heat and pressure. As a result, anthracite contains the highest percentage of carbon and the lowest percentage of moisture. Anthracite makes up only a small part of the world's supply of coal. About half of coal's reserve is bituminous coal. The remaining coal reserves are even softer. How coal is formed. The formation of coal dates back to million years ago, when the earth was covered only with vast moist forests having huge trees, shrubs, ferns, etc. These plants underwent their life cycle and withered away, eventually falling back to the ground, most of which were swamps. New plants replaced them. They underwent a life cycle and whole process continued repeatedly over the years, as a result of which the earth beds started accumulating all dead plants. This gave rise to a very thick layer of dead decomposed matter packing down plant matter, washing away all the decayed matter. Physical and chemical changes took place and the result of heat and temperature extracting out all oxygen, leaving the plant layers with carbon-rich content, thus resulting to the formation of coal over a period of time. Petroleum. Petroleum is also called crude oil. Is a fossil fuel. Like coal and natural gas, petroleum was formed from the remains of ancient marine organisms, such as plants, algae, and bacteria. Over a million years of intense heat and pressure, these organic remains or fossils transformed into carbon-rich substances we rely on as raw materials for fuel and wide variety of production. Formation. The geological conditions that would eventually create petroleum formed million years ago, when plants, algae, and plankton drifted oceans and shallow seas. These organisms sank to the seafloor and end their life cycle. Over time, they were buried and crushed under millions of tons of sediments and even more layers of land debris. Eventually, Asian seas dried up and dry basins remained, called sedimentary basins. Deep under the basin floor, the organic material was composed between Earth's mantle, with high temperature and millions of tons of rock sediments above. Oxygen was almost completely absent in these situations, and the organic matter began transform into waxy substances called kerogen. With more heat, time, pressure, the kerogen underwent process of catagenesis and transformed into hydrocarbons. Hydrocarbons are simply chemicals made up of hydrogen and carbon. Different combination of heat and pressure can create different forms of hydrocarbon. Some other examples are coal, peat, and natural gas. Sedimentary basins where ancient seabeds used to lie are sources of petroleum. In Africa and Niger Delta, sedimentary basins cover land in Nigeria, Cameroon, and Equatorial Guinea. More than 500 oil deposits have been discovered in the massive Niger Delta basin, and they comprise one of the most productive oil fields in Africa.